With those decisions, we obviously need a set of actuators in the storage systems themselves and in the memory hierarchies to go and make changes. So these are parameters that already exist in the vast majority of storage systems. And some of them, for the first time, even though we've known about those parameters being important, we have tended to, in the storage industry, implement those as lab optimized and lab tuned and not really dynamically tuned, even though those parameters might exist in the code of our storage systems. So now we want to move towards being able to have a larger number of actuators that influence the different behaviors of our storage systems and make them available and expose them to this new OODA loop, which allows us to take the decisions to use them to enforce SLAs and to optimize and again, continue to turn those knobs to hit our desired outcomes at the lowest possible cost. So once those actions have been implemented in the system and sent dynamically over to the source layers which have implemented them and the system is starting to adjust, again, we receive new observation and we update our models and we decide. Now, this sort of a loop for a high throughput system like a storage system, which sits underneath pretty much all of computing, and so therefore has to be exceedingly efficient. This type of an OODA loop with instrumentation, model predictions, and control actuation software has, up until very recently, been not really feasible because of the cost associated with each of those OODA loop steps. However, we have recently achieved the ability to start to take each of those pieces and make them more and more and more efficient. And we expect that will continue. So now we believe we're at a stage where this ability now becomes real because we can do this and with costs that are sitting down in the tens of nanosecond scale in terms of overheads and not in the hundreds of milliseconds or seconds scale that are present in other types of systems that don't have the real-time mission criticality that a storage system obviously has to be able to provide. So a fully autonomous storage system and memory hierarchy obviously has to be self-aware. We've hinted at this earlier. Now, in a modern system, we are dealing with a distributed system. We have applications, containers, databases that are running on distributed platforms. And there are lots of different underlying infrastructure components, both hardware and software, that provide various storage and memory services. These include servers that have CPUs that have memories, L1, L2s, LLCs of various sizes, flavors, and forms with different latencies and performance characteristics. Obviously, we have buffer caches and anonymous memory management in DRAM and increasingly so in other systems like 3D XPoint, MRAM, and other emerging technologies. We have fast flash, we have slow flash, we have all of these components sitting in distributed systems and with very elastic network caches actually sometimes available before connecting to network storage. So, we have caches and we have disks and we have flash and we have DRAM all throughout these layers. And even in my smartwatch that I wear every day, right, there are numerous layers and tiers of storage, oftentimes hidden in plain sight. A fully autonomous system that manages a memory hierarchy like the one I've depicted or a simpler or a more complicated one has to be self-aware to be able to continuously answer many different questions in those OODA loops, okay, to be able to maintain the integrity of the system, QoS constraints of the system, as well as the cost and performance of the system. And I've just listed just a small number of them. These particular ones are oriented more towards performance, which is an area of focus for me. So there's a little bit of a bias there, but we can easily talk through the durability, availability, and other constraints in storage systems. So is the performance being achieved in the system good? If you could improve it, what are the avenues available and what are the cost benefit of those avenues to be able to improve the performance? Can knobs be tweaked for these? How much occupancy in the various tiers, tier 0, tier 1, tier 2 of these memory hierarchies? Again, oftentimes these hierarchies are sitting and hiding in plain sight. How much of those tiers should be allocated for different applications and workloads and so on and so on? How do you achieve high percentile latency for the more critical applications? Again, in my smartwatch, we'd want the background tasks to still be able to access resources, but not at the expense of the foreground tasks. What if analysis of workloads so that we can do initial placement and load balancing and so on, right? So these are the classes of technical low-level questions that a self-aware autonomous system needs to be able to continuously answer. And if we're able to do some of those things, what are the types of use cases that we could offer? Right? I just picked two, and I'll go through them. There are many more, and due to limitation of time, I'm focusing once again on the performance autonomy type of features and use cases. So the first one I want to talk about is autonomous quality of service and SLAs. And the most sort of holy grail in this field is latency guarantee. Could you take a storage system and dial in a certain number of milliseconds, let's say, of a performance guarantee at a very high percentile, let's say. And if you could do that, what is the use case for that? So here, the use case really involves a bunch of value propositions around this core capability of a user being able to dial in a latency or a throughput target and some sort of a dollar budget and have the autonomous storage system and its internal memory hierarchies auto-allocate the right amount of capacity to be able to hit those SLAs. Now, the value is quite tremendous here, right? For the first time, we'd achieve complete automated SLAs. if we had such a fully autonomous QoS system. The ease of mind associated with this set and forget. Now, this type of set and forget does exist in the world of CPU, for example, and many CPU scheduling systems provide us these SLAs and SLOs. And we've seen in the market billions of dollars of transactions happening with enterprise customers purchasing software that allows that ease of mind and set and forget quality of service guarantees to exist for CPU. However, we've not been able to, because of the complexity of memory hierarchies and storage, to be able to achieve that yet. So here, we could, with a fully autonomous system, provide that, right? And continuing down with the value props, this sort of thing would allow higher margins because you can do more consolidation or sharing of resources while still being guaranteed that the critical functions achieve the latencies that have been specified. And so this then leads to revenue disruption avoidance, among other things, and performance scaling that really boils down to achieving asymptotically zero OpEx, because it's just a matter of dialing into the storage system the desired policy around what the QoS SLA should be, let's say in this case with latencies or other metrics, and the system dynamically adjusts itself. And if there's not enough capacity, it informs you. But at the end of the day, the OpEx associated with it, especially in a cloud or scalable context, is approaches zero. Another really interesting use case is having the system come at it from a different angle, which is autonomously optimize the cost or performance, whichever is the primary driver business objective function. So here, using real-time workload modeling and resource allocation predictions to be able to dynamically adjust resources and provide isolation among the different clients of that and users of that storage system, and really achieve the completely autonomous right-sizing dynamically for all of the tenants that are hitting the system. Now, if we were able to achieve this, the value propositions, again, are fascinating, right? That we could achieve provably optimally lowest total cost of ownership for whatever the workload that the customer throws at this system. And that workload could be something we've never seen in the lab, but a fully autonomous system is able to navigate and figure out exactly how to drive the TCO down to the lowest possible level. We could use this system to eliminate noisy neighbor problems, which again is a huge OpEx reduction for infrastructure teams in the enterprise. And so on. So policy-driven operations and predictive planning, and being able to have the fully autonomous system plan itself on its own much further ahead than we're able to do today, so that the appropriate resources can be allocated well in advance with enough heads up to be able to actually receive and implement those additional resources. In part two, having seen the use cases and the opportunity and the value propositions and the vision around fully autonomous storage, we can now look at some of these technical breakthroughs that are enabling in the specific area of performance autonomy, which is an area that I'm focusing in the interest of time. So modeling performance in real time is a new area of some breakthroughs which are enabling low-cost, real-time, efficient, and accurate modeling of storage systems with millions of IOPS has traditionally been not possible in real time. Even offline has been exceedingly expensive, so that even if you were able to learn the system well offline, you run the risk of the actual dynamics of the system having changed dramatically by the time that you have learned the behavior of the system, and now your learnings are stale and it's hard to justify implementing those in a loop. So here, this task is really about learning the performance model of the joint model of the workloads, the applications, and the storage system, and how they interact with each other. And if we're able to do that, lots of different flavors of models can be built, but fundamentally, they're all just functions of the workload, the resources available, and the parameters of the storage system. And so on the right-hand side, I've again zoomed in a little bit on a bunch of these models and some input workload characteristics that lead to those models that allow us to navigate. These basically serve as GPS and can be fed back in to our prediction systems that can then go and take specific actuation changes. If we can model storage performance in real time, we gain a lot of these capabilities. So, but what are these performance models? So here I have taken just a single dimension and I have simplified it down to latency, so lower is better, and the cost of the aggregated resources allocated to the storage system to achieve that latency for a given workload. So this right here, the red curve, is a real customer's real production workload. You notice that as we add resources, which is on the x-axis towards the right, if we're adding cost and dollars, that performance does improve. Latency does decrease. But the interesting challenge that has been well known in the storage world is that the improvement in performance, or in this case, lowering of latency, is not a linear function. It has all these step functions in it, all these cliffs. And there are plenty of times where you could 2, 3, 4x the resources that are allocated to a particular application or workload, or a combination of applications and workloads without much increase in the performance. So here in this example, which again is a real customer production use case, if we increase the cost of the system by allocating more of the tier 0, tier 1 storage by 2x, and now having double the budget. Imagine going from $1,000 a day for this workload to $2,000 a day and not seeing any interesting performance improvement. And we might then go and try to take it to 3 or 4x. We still wouldn't see a performance improvement for this production workload. Maybe we're bold enough, we'll go to 8x. At some point in time, we will give up. I would give up at 8x if I was doing this manually. And if I give up at 8x, now I don't realize, but I'm actually at the cusp of a fairly steep improvement in latency if I was to just continue to increase the resources that I'm giving to the system. Now, again, today we don't have access to that red curve. Only a fully autonomous system has access to that red curve, and then the ability to make decisions based on this, right? So in this particular case, it was perhaps better to not expend 8x the resources for no performance benefit. Another way to think about this is, suppose you're currently sitting at this other point where you're at the cusp of performance improvements, right? This point, turns out, for this particular workload, is actually the least efficient point to operate, because had you allocated 1/8 the resources, you would have achieved the same performance. And had you allocated just another 30% of resources, you would have had a precipitous improvement in lowering of latency. In other words, you always want to operate at the bottom of these cliffs, at the talus of these cliffs. And if you're able to do this in a fully autonomous system, you can now have a very useful, powerful trade-off, which allows you to trade off cost and performance dynamically based on the requirements and needs of that workload. But again, this is only available in a fully autonomous system because the system is quite dynamic. You cannot just statically do these things. If you do, you will very quickly end up in QoS violations. So this is a very quick overview of just one dimension of these autonomous performance models that can be constructed, and the ability to be able to construct them is net new. You're hearing about this probably for the first time. That's how fresh this research is, and this involves several peer-reviewed papers that can be referenced and found at Unix ATC, FAST, and Sigmetrics that have created the ability to build these types of models in real time. Now, here are some sample models for production applications. I'm highlighting T09 here. Again, customer workloads. So the names of the customers and their workload identity has been elided here. And in this case, you'll see 120 gigabytes worth of resources allocated to the highest tier before any performance improvement is seen. So again, just imagine going from 10 to about 130 before seeing any performance improvement. That's a 13x increase in the physical resources. And very few of us would have the patience to really search that space manually, because again, that red curve is not available today in our traditional systems. So that red curve is the internal representation of the autonomous performance model that a fully autonomous device has access to. And this is the stuff I'm extremely bullish and excited about. I think we're at the cusp of a major revolution in how storage systems are built because of these capabilities now finally become available in terms of the underlying computer science and mathematics. So for T09, you really don't want to allocate pretty much anything more than a few gigabytes of your most expensive tier unless you're able to afford to go to 130 gigabytes or your SLA requires it. On the other hand, we have T15, and T15 gets all of its benefit in the first couple of gigabytes of the most expensive tier of memory, and you can give it as much as you want after. It's just going to flatline. And so imagine co-locating T09 and T15, we would be able to reason through a fairly simple logic and a very simple heuristic on how to allocate resources. Obviously, you want to give your initial set of resources to T15 and all the remainder to T09 until you get to about 130 gigabytes. At that point in time, perhaps you have a T20, and now you can start to allocate the next set of resources to the T20 workload, because that particular workload, interestingly, benefits from each additional megabyte of memory you give it. So this is the types of trade-offs that can be accomplished for the first time. Understanding this notion of a fully autonomous adaptation takes a moment. So I wanted to start off by talking about it at a very abstract level. Imagine a hypercube. Now, in this particular case, we've just brought it down to 3 dimensions. And this hypercube is showing us a bunch of different parameters of the system. An example of this could be a read-ahead parameter. Another could be cache block size. Another is size-based partitions, like say in a memcached-like system, or size-based allocation strategies. And usually most storage systems have several dozen of these parameters, each with a certain range of values. But to be able to fit it on a 2D plot here, I'm just showing a 3D model of this. Each dot represents the optimal policy for a single workload. Of course, there's millions of workloads out there. So if we were to kind of draw out a manifold of those, this is this type of graph that we'd abstractly get. And so each of those points then is the 3 tuple of parameters 1 settings and 2 and parameter 3 settings that result in that particular workload ending up with its optimal performance. Now, as you can see, workloads have dramatically different optimal policy points and parameters. And these today we set as a one-size-fits-all. And of course, it is not true that one-size-fits-all, but that's what we do. We do it in the lab, and we ship our systems based on sort of the least bad combination of our parameters based on performance experiments done by our brave performance engineers who are running these workloads, running benchmarks, and studying customer environments when problem reports come in to try to guess at the optimal settings. But all of that is being done at design time. Now, that design time effort does pay off. A well-tuned system out of the box is better, way better than an ill-tuned system out of the box. So there's no knocking that. However, a huge amount of opportunity and performance is left on the floor because of the wide variety of workloads and their characteristics for which we could actually, if we did it in the field in a fully autonomous system, adapt. So now with that abstract background, let's look at a very specific example. So this example, we have the same workload for which we are plotting these performance models. And what we're seeing is that depending upon different parameter settings of the underlying storage system, in this case, you see, for example, you see a purple and a blue and a green and a dark green and a red. These are actual performance latency behaviors of the same workload just run with different parameter settings. And you can see how big the difference is. It's easily a reduction of 50% in latencies depending upon which parameters you pick. Now, the question is, how do you pick this? And of course, a different workload will have completely different shape. So how is it that we are going to pick these? So this is where a fully autonomous system that is able to do real-time modeling and become self-aware can do what-ifs on these in real time, given the latest technology that we have available to us, and then reason through and dynamically adjust these parameters to hug the lowest possible curve across all of these, right? And dynamically switch between parameters based on the conditions, both internal to its system as a self-awareness, as well as in the environment from the workloads. So this is a high-level overview of what adaptation would look like in these systems. Now, here's some real data for what the adaptation can give us in terms of some performance improvements. So on the top row, we're seeing a latency ratio against between the best and the worst case, the latency ratio of different allocations provided to different workloads for a given cache system, in this case, multi-tier cache system. So now what's happening is the black lines are the envelope of the best and the worst possible performance that could be achieved. And the red line is dynamic adaptation of an algorithm that dynamically is figuring out what's going on. Of course, the black lines are not dynamic, they're offline. We just run offline workloads to figure out exactly what's the best possible, what's the worst possible that could happen. And of course, lower is better. So here what we have is, in the red line, a system that does not have any hints other than really trying to understand and become self-aware. And we're evaluating the performance results that we have seen around those, right? So we've seen up to 69% of potential gain for Lears, which is a very powerful eviction system. And then plain LRU, we've seen 50% improvement. 50% of the potential gain was able to be captured by the dynamic adaptation systems, in the case of LRU and so on. The lower row is a very similar type of experiment, but now changing parameters, very specific algorithm-specific parameters, and not just optimization parameters that we've added to the system as part of the knowledge gain that a fully autonomous system is able to utilize that other systems cannot. So the bottom row is more standard prosaic parameters that already exist in, for example, 2Q, layers, etc. And we're iterating over those parameters. Again, you can see that the dotted lines are the offline determined best and worst, lower is better, and dynamic adaptation system operating in real time at nanosecond level costs, tens of nanoseconds costs per IO, is able to achieve self-awareness and hug very close to the best possible performance in most cases. So this is the results that we're seeing in how these systems are behaving with field workloads. In the interest of time, I'm going to skip going over details here, but this is an example of, again, something that only a fully autonomous system can do. This simply cannot be done at design time or in the lab. This has to be done in the device at runtime. So here what's happening is that a fully autonomous system can achieve a very interesting set of optimizations which have to do with thrashing mitigation. And thrashing is something that's very hard to define at runtime, but if you're able to build these real-time performance models, you can detect it and take certain evasive maneuvers. And those evasive maneuvers basically take the purple point that is currently operating at about 45% miss ratio and actually drive it to the convex hull by doing a very clever curve steering that can only be done if real-time models are continually updated. So here, we're able to actually do curve bending. This is the very first time curve bending has ever been possible in real time, where we can take the actual customer workload that is hitting the storage device and understand its intrinsics so carefully that we can divide the workload into more than one class and do it completely dynamically and tweak those classes separately from each other and achieve an overall completely new operating regime. And so, in this particular case, this is with a tier 0, tier 1 type of cache. And I always talk about how caches are already acceleration. So how do you, talk about the acceleration of an acceleration? Is that acceleration squared, right? Because we're taking an acceleration tier and we're actually dynamically changing its conditions so that the accelerator gets a second layer of boost, right? A second booster rocket, if you will. So as you can start to get the feel of fully autonomous systems actually being able to do things that simply just could not be done before, right? Again, these are things that are different from other domains like self-driving cars, where a really attentive driver can accomplish most of the things that a self-driving car can. But in the world of storage systems, a really attentive operator simply cannot do certain class of things that a fully autonomous system can. And now we sit at the cusp, what I believe could not just be incremental improvements in efficiency and performance, but order of magnitude jumps in performance and cost improvements because of fully autonomous storage systems. So remarkably, we can use the same sort of technology in fully autonomous storage systems to achieve QoS targets. So for example, this red curve, which you've seen in one of the animations earlier in my deck, that it is actually a very dynamic curve. So I'm just taking a single snapshot of it and showing it here. But that dynamic curve, we can model that curve as a self-awareness mechanism inside the storage system and be able to understand exactly what the various dynamic autonomous tier allocations need to be for this workload to achieve any arbitrary performance target. So again, this is an industry first. It's never been done before, to be able to take a 95th percentile, for example, or 99th percentile target that a user sets for a workload. In this case, I'm giving an example of 7 milliseconds, and have that be dynamically enforced by the autonomous storage device by varying the allocation tiers constantly to always fit just the right amount of the working set of the application to be able to hit those SLAs at arbitrary percentiles. So this is, again, something that could never be done without fully autonomous systems. And finally, multi-tier systems are the norm now, as we've already discussed. So how do you allocate across these tiers for a given workload to achieve the cost and QoS targets of that workload? And again, a fully autonomous system is able to do that multi-tier allocation. So hopefully this gives an idea of how I envision and how we're working together as an industry on across these various components, across the various areas of performance management, which can be done autonomously now with the latest tools available, but requires a cross-industry collaboration to be able to build those actuators and those hook points and the instrumentation points to be able to do it efficiently and to be able to do it at scale, in the context of millions of IOPS and in the cloud scale. And then also to rally ourselves together so that we can build standards around durability and availability standards around autonomous behaviors of systems and the specification languages for that and so on. So hopefully we can come together and build the consensus around these concepts and ideas so that we can start to build a system that in the end game is able to finally deliver a completely lights out, self-managing, policy-driven system to the world of, to the storage industry, to the memory hierarchy and database industry. And if we're able to achieve that, we will finally be able to throw away all of our control knobs and have the system manage those knobs themselves, and to finally be able to throw away the steering wheel and allow the system to operate itself based on the constraints that our customers provided. I hope this was useful. I look forward to collaborations across the industry around this. Please get in touch and look forward to fruitful conversations. Thank you very much. My contact information is Irfan at Magnition.io, and you can find me on Twitter at virtualirfan. Thank you so much for attending.